Morning, everyone. So today I will talk about attacking the VxWorks OS. So little presentation. So I'm Yannick Formaggio. I'm security researcher at Estuary Innovation Labs, which is a startup company in Vancouver, Canada. So you can find me on Twitter by the handle Lumberjack or Yannick Formaggio on LinkedIn. My hobbies are looking for vulnerability using fuzzing techniques. I'm a Lego fan, and today is my first public talk. So, yeah, thank you. For this project, I had some help from my coworkers, Richard Su and Eric Liu. Eric is the lead security researcher of the lab. So today I will talk. So I will do a little introduction about VxWorks OS and what has been done previously. Then I will try to go deeper inside the VxWorks memory management and some memory protection. And then I will elaborate a story of what research we did. So we're starting from fuzzing to discover vulnerability, to finding a vulnerability, and then trying to exploit it. So what's VxWorks? For people who don't know what's VxWorks, it's the #1 embedded device real-time OS. Wind River claimed it's over 1.5 billion device that runs with VxWorks. And it supports a lot of CPU architecture, so x86, ARM, x86-64 recently, MIPS, PowerPC, and so on. So I wanted to verify if we could find a lot of VxWorks OS. So as you can see here, we can see 123K VxWorks device facing the internet. So mainly it's VxWorks 5 version and some VxWorks 6 as well. So let's go back to VxWorks. So it has been first released in 1987 with nothing fancy features, so just 32-bit processing. Then in the 90s, VxWorks 5 has been released, and it was the first real-time OS with a network stack. At this time, no specific security features was implemented inside VxWorks. Then in 2000, you can see the release of VxWorks 6 version in December 2004. This version came with some security improvements. So, for example, real-time process and that no more task shared memory. So every task is segregated. And then recently in 2014, VxWorks version 7 has been released. So new feature is supports for 64 bits instructions, and they added way more security inside it. So you can find VxWorks in different domains, so automobile, aerospace and defense space. So you can see the Mars rover, for example, runs with VxWorks. Some robotics as well, network equipments, could be VoIP phones. And you can find as well in some Airbus aircraft. And so I talked about the last one, the VxWorks 7, and they claim it's the OS for the new trend, Internet of Things. So, sorry. Next, I will talk about why we choose to study VxWorks and what's the point of what's the security feature we can find in it. So here you can see that VxWorks has not much vulnerability, so just 12 CVE has been issued. 7 of them are just denial of service, and one is code execution. Sorry, and you will see later I will add one, but no CVE created for now. So VxWorks and security. So we know that Wind River treats the VxWorks security seriously. For example, in 2011, they announced a partnership between them and McAfee company to improve the security of the OS. And I told you before that the version 6 introduced some memory protection. I will come back to this after. And 7.x as well, so for example, digitally signed modules, encryption, password management. They now store password with SHA-256 algorithm, and some other stuff. So what has been done before and what inspired us for this work, for this project? So first, the talk from Formaggio about shiny old VxWorks vulnerabilities in 2010. So Formaggio highlighted the fact that there was a problem with the WDB RPC. So I will just introduce briefly what's WDB RPC protocol. It's basically a debugging interface between used by the developer to debug their task applications and stuff on the VxWorks target. So he implemented 4 Metasploit modules that use this WDB RPC protocol. And then he found that the password was stored with a very, very, very weak entropy. And we were able to reproduce this attack by creating a rainbow table with around 200K hash passwords. And with this, you can crack any password on the VxWorks OS. Then the talk about dev TTY0, not the talk, the blog article, reverse engineering VxWorks firmware. So it was just to have some knowledge about the OS. And then after this, a white paper from Aditya K-Sud from Seknish, who detail a bit more the WDebugging interface and introduce some OS security feature. So now I want to talk about what's inside VxWorks and specifically the memory layout and the protections they implemented in it. So why I want to talk about this? Because you know that most of exploits use the memory to spread. So here I just choose to talk about the x86 memory layout because after I will show you what we did, and we used the x86 architecture for our work. So you can see here, so the address starts and are relative to the local mem, local address variables that you can set when you create your VxWorks project. And then, so you have first the interrupt descriptor or vector table, which store any interruption and exception pointer as well. And you can see it has the interrupt stack associated with it because starting from version 6, the interrupt stack is totally segregated from the other stack. Sorry. Then here, I just highlighted this guy because when there is an exception occurring on the VxWorks, it will display a message regarding the severity of this error, and some of them are stored in this memory area. Then here, highlighted in green, you can see the entry point of the VxWorks OS, and then some other memory address. And as I talk about the WDB protocol, here, this protocol has a specificity that he shared this area of memory with every task, every processes on the VxWorks OS. So VxWorks provides some MMU-based feature in addition to the virtual memory support and some non-MMU-based protection for the heap. So I will detail some of the protection. So here you can see the task and interrupt stacked overrun and underrun detection. So what they do is they they allocate some memory before and after the stack of the task, for example. And those memory area are non-readable, writable, or executable. So when you try to read them, you will raise an exception that will be catched by the OS. Then they also introduced the non-executable task, and non-writable text segment. So in red, you see that the text segment of the program is read-only, and the data segment is read and write. And also you have to know that starting from VxWorks 6, all the task stack is not executable if you set this parameter include task when you when you create the project. And then one last memory protection. So to detect the null pointer usage, they set the memory area starting from 0 to be non-readable, writable, and executable. So when you try to read or access it, it will raise an exception. And we saw a lot of exception when we first VxWorks OS. And so next I will talk about the heap protection. So basically the first one you can see is almost the same as the stack protection. So they just add some memory area before and after that if you access them, you will trigger an exception. And the second image just to show that each task has its heap, and you cannot overrun on the other heap. So now I've talked about this. I will talk about our main work on this project. So I will talk about from fuzzing to exploit. So we did this project first because one customer asked us to do a pen test on this VxWorks 5 and 6 version, and he provided us some pre-configured OS image and tools with some network protocol activated. So first port map, FTP, TFTP, and NTP, and other protocol as well. So we did some fuzzing on it. For this fuzzing, I used my favorite fuzzing framework, which is Sully. But if you're familiar with fuzzing, when it comes to fuzz a non-conventional OS, I would say, you have to find a way to detect accurately when the target crashes, to know when you want to reboot the target, etc., or to have some more information about the crash. And so, well, after some research, we decided to use the WDB RPC protocol like the VxWorks developer do. So the problem is the only implementation that we found was the one from, the only open implementation we found was the one from HDMore, but it was in Ruby. and not as complete as I needed for my project. So we decided to re-implement the WDB RPC protocol in Python to be more to interface easily with SLE. So yeah, so I told you that WDB RPC is the debugging interface used by the VxWorks developer to debug their apps or tasks, etc. It's a service running on port UDP 17185, and if it's open, you can execute whatever you want on the target. So anything, you can read, write memory, execute some code. So you own the system with this. And this protocol was based on the Sun RPC protocol. So how it works? So on the left side, you have the host side, so the PC, for example, and on the right side, the VxWorks target. So running on the host, there is a target server which communicates with the target agent using WDB message. And this communication could be on different transport layers. So it can be done on the RPC, I told you. You can use a pipe as well, serial port, and you can implement your own solution. But both the target server and target agent has to know how to use this transport layer. And then when the target server is connected to this target agent, you can use some other tools provided by the VxWorks development environment. So, for example, a shell debugger, etc. So what interests me here is mostly the debugger part. I decided to show you how the packet structure is, because there is not much information, open information on the web. So as I told you, it's based on the RPC, Sun RPC protocol. So you can see you have the IP header, UDP, and then the RPC request header for the call. So the call message are the message sent by the target server, so from the host. And then you have the XDR encoded stream. So XDR is just packing some integer and strings together. And three first fields of this XDR encoded stream are the checksum, the length, and the sequence number. So the checksum and length, the checksum is computed only from the XDR encoded stream, and the length as well. But from the length you remove 4 bytes. I suppose it's the sequence number, but I'm not sure. And then you have the reply from the target agent. So here you can see just two major differences. The RPC reply header is only 24 bytes. The last field of this header contains the error message, if there is any. And there is another error code in place of the sequence number, as you can see here, but this one is just for WDB errors. And you will see after that this error code is important. So now that we have some basic information on WDB, I want to talk about how to debug. Oh, thank you. How I managed to debug the VxWorks target. So what I did, I just do some network protocol reverse engineering. So what I did, I connected the VxWorks development environment to the target and see what's happening when I do some actions. And so then I have this diagram here. So on the left you have the host, and on the right the target. And so to debug the target, you have to follow certain steps. First step, you have to connect, normal. and yes, the target reply you if it's okay, you can connect, and then there is a slight difference with conventional debugging, I would say, because on the VxWorks 5 and 6 version, you have to set the you have to set the task you want to debug to be breakable, because by default they are non-breakable. So if you try to put a breakpoint on it, you will raise an exception for VxWorks 5. For VxWorks 6, nothing happened, but yeah. So here is so you have to call a specific function inside the memory of the VxWorks OS using this WDB function call message. So yeah, you acknowledge that if it's okay. And then you can start to attach to the process. So there is, on VxWorks 5, there is 3 steps to attach to the process. So first you have to suspend the execution of the task you want to attach to using the WDB context suspend, and then you add, I would say, a breakpoint at the entry point of the task using this procedure call. And then you say, as you suspend here, you have to continue the execution to be able to debug it. So you send the WDB context continue message to the target. On VxWorks 6, they introduced some new procedure, so it's slightly different. So the first one, not very original, just they use the WDB target connect to. So the only difference it adds in the payload a way to identify the host. So just a string saying you name whatever you want. And then so again the function call to set the target, the task breakable. And then the new difference now, it's instead of using the context suspend, event point add, and context continue, they use the evaluate gopher several times. So what's gopher here? It's a small interpreted language. So it has two objects, so the pointer and the tape. And so you send some commands, so it's like a script, I would say. And the target will answer with the pointer to the memory area where the result of the command is. And then when you're done sending the evaluate gopher, it will send you the final result, and then you will be able to read from the memory that they pointed you the exact result here. So it was weird to see this because evaluate gopher just gives you some information and not actually put breakpoint or attach to the process. But anyway, it works like this. So now we know how to attach to the target. What we want to know is when a crash occurs, how to detect it. So on VxWorks, when something happens on the target sends a message on the same port as WDB RPC, but totally, it's not random. It's just all the messages are like this in VxWorks 6. And for VxWorks 5, those 4 bytes here are equal to EE as well. So when the host receives this message, he knows that there is something wrong on the target, and then he has to send the WDB event get to acknowledge this message. If you don't do it, the target will keep on sending the event notification, and you cannot do anything else. And once you acknowledge this message, you can ask for more information about what happened on the target. So, for example, you can get what the content of the register, sorry. here and read some memory around the crash area, for example. So you can disassemble after to do post-mortem analysis, etc. And you can, in this answer, I forgot, they will give you the exception number. So it gives you more information. So now let's talk about the framework I implemented. So this framework, as I told you, is in Python. For now, it supports only VxWorks 5 and 6 version, but not all the protocol, because I don't need everything on the WDB RPC implementation. You have to know that I think there are more than 50 procedures, and as you can see, I don't use 50 different procedures here. And it implements a basic remote debugger as well. I named it WDB DBG. Not very original. This framework has some external dependencies, so I needed PyF tool to read the VxWorks image. The VxWorks, so basically it's an OS image that you compile when you create the project. And it contains, so when I do this, I can read all the imported function. So for example, when I use here, the WDB function call here, I need to provide him the address, the entry point of the function I want to call on the target. So PyF tools and let me do it. And then I used Capstone engine, to disassemble the code around the crash area. But for now, this feature is not fully implemented in the framework. So I told you I use the Sully framework to do my fuzzing. So now I have to find a way to interface with it. So in Sully, if you don't know, you have this script, process monitor.py, that's process monitoring for Windows targets. So I just use some of the method here, implemented here. For this, I implemented a debugger thread class that instantiates the WDB DBG in a thread, and just one callback to detect when the crash occurs. And I also implemented another class that's called process monitor ped RPC server. So in Sully, the original author, implemented his own RPC protocol to call the function on the different script he had. So I have to implement this part to communicate with it. And then the VxMon class that wraps everything. So how everything interconnects now. So here, so the Sully fuzzer, so my fuzzer script for any network protocol. The VxWorks target is here, and the VxWorks process monitor, so the one I told you before, that use the WDB DBG framework to debug the process on the target. So between VxWorks process monitor and target, we use the WDB RPC protocol. And between VxWorks process monitor and the Sully fuzzer, the ped RPC protocol, because for now I have no choice. So now I will just show you one demo. So it's just a video because the setup of everything is very long, so I don't want you to wait for it. So here are the results. So in this corner, Sorry, I can't see. So you see here the VxWorks OS running inside VMware, and SOLI monitoring interface, which is a web interface. Here the VxWorks monitor that will at some point detect that there is a crash occurring on the target. The other windows are just network monitoring, VMware virtual machine monitoring as well. So this window will help me to reboot the VMware and restore the last snapshot. And here just the SOLI fuzzing script. So here you can see when he detects a crash, he stores the information here and reboot the VxWorks OS automatically. So, and then you can continue automatically to fuzz the target. Okay. Okay, so here you can see that we found a lot of different crashes, but it's always the same crash, but occurring on different port map procedure. And so now I will talk about the crash we found and how we analyze it. So we found that when you use the port map protocol, which is transported by RPC protocol, we trigger a crash by setting the credential flavor, which is a field of the RPC header. When you set this value to a negative value, it will crash the VxWorks here. So you have, just for you to know, the credential flavor is used in the authenticate_authenticate function here. It tells how you have to authenticate to the process. So there is 3 different ways to authenticate, but I will come back after. So here is the disassembly code of the authenticate function, and I will show you why and where the crash occurs. So here you can see that they store some parameters in EAX, and then here they store the credential flavor value inside EBX. And then you can see that they compare EBX with the value 2, so the 3 different methods to authenticate. And depending on this value, they will jump or not at the address after. But as you can see, the jump is a signed jump. So it seems like it's integer overflow. So so when we set this value to negative value, what happens? It's never greater than 2, so it will never go to the branch and continue its execution until this line here, which is a call inside the function table. And they use directly EBX value to call the correct function. So I will just show you how this function table looks like. So here you see there is just 3 functions. So the first one is no authentication. The second one is use the Unix authentication. I didn't display the whole disassembly. And the last one is SVC or short. But as you can see, it does nothing but returning 2. So I don't know what's the point of this short authentication. So before I show you how we exploit it, I will just tell you that we reported this vulnerability to Wind River on July 22nd, and they acknowledged it pretty quickly on the 23rd. they confirmed the vulnerability on the 11th of August. This vulnerability affects the VxWorks version between 5.5 and 6.9.4.1. They announced me yesterday that they are providing the patch for this vulnerability, but they will not do a public announcement or create a CVE for this because they think it has not a big impact on VxWorks target. And you will see that they are wrong. So they asked me to announce that every VxWorks customer should check their knowledge base for details on how to patch the vulnerability. And yeah, I want to mention that I have been authorized to disclose every details I will show you after. So as I told you, we have here an integer overflow, and we were able to do a remote code execution using this vulnerability. So just for you to know, it works on VxWorks 5 and 6, but I will just show you the VxWorks 6 version because they implemented some security feature, etc. And I will show you that with this exploitation, we bypass any memory protection they put. So if you remember, I told you that the stack is not executable. The text segment is read-only. The data segment is read and write only. But what about the heap? The heap has nothing, no protection, no specific protection. So what we did, we heap sprayed the shellcode using the port map protocol. So we just send our shellcode as a RPC payload. And then when the heap spray is done, what we do, we have to compute the credential flavor value so that we can, when the authenticate function reads this value, it will jump inside the memory area where there is a pointer to where there is the address of an area between where our shellcode has been sprayed. So we managed to find that at every reboot, the address are slightly different, but one area is always the same. So we try to find an address that jump inside this area, and then we have our exploit. So I will show you what we did then. So I will start the VxWorks 6. So it's paused. I'll just reboot it, but just so you can see the boot process. Okay. Okay. So just who am I? So you can see the user is target. So it's the default user on VxWorks, and I will. Using my exploit, I can see. I'll see. Oh. The demo effect. So what I did, I just added an account which is named AA with the password ASDF, so very simple. And to show you that the target is still running, I just run the function that's called task show. So it's show all the task information and memory address. So yeah, and now just to show I will connect to the target. I can't see. No, sorry. So what I did after, you can connect to the target using these credentials, and you have you can control anything on the target because you run everything with the highest privilege on the VxWorks. So you can edit the boot line. You can do whatever you want on this target. So yeah, I think I'm done. So if you have any question.